Hi, my name is Sadie Martin, and this is Lab 4, Oscillations. In this lab, the motion of an object attached to an oscillating spring is analyzed and observed. A computational model will then be used in order to measure the change in energy of the system while measuring each energy specifically as well. The update position and velocity formulas derived from Newton's second law are used to calculate and change the ball's motion. In order to do these calculations, I need to find the net force acting on the ball, which is the sum of the force of gravity and the spring. In addition, the change in energy is found for kinetic energy, gravitational potential energy, and spring potential energy. Now, using the energy principle, taking the ball, spring, and earth all into one system, this causes the total amount of work to be equal to 0. Therefore, the sum of all of the changes in energy is equal to 0. Here is the analysis of the mass's motion. This video was provided to us, and I set the origin for the coordinate system to be at the fixed end of the spring. Therefore, the object's position would be in the negative y direction. Not shown in the video, I also set the calibration stick to be the original length of the spring before oscillating. Here is the code for my computational model. We were given the starter code and I inputted the values necessary. The mass of the object was edited to be 0.402 kilograms. The position of the object was also edited to match the object's initial position from tracker. To the right, the relaxed spring length and the spring stiffness were calculated. To find the stiffness using periods of oscillation, we were able to rearrange the formula to solve for the stiffness as shown. The outcome came to be 6.0175 newtons per meter. For the relaxed length of the spring, since we can say that the magnitude of the force of gravity is equal to the magnitude of the spring force, we can obtain an equation to calculate L naught, which came out to be 0.0453 meters. Finally, using the formulas introduced at the beginning, I edited each system energy and set the total energy to be the sum of all individual energies. For the calculation loop, I first changed the time interval to go up until 9.510 seconds, which reflects the time where the object is in its final position in tracker. Then I calculated the net force by editing the force of gravity to represent mass times the force due to gravity in the negative y-hat direction, and editing the spring force with its respective formula. The sum of both of these forces is equal to the net force. I then edit the object's position and velocity by inputting the update position velocity formulas derived from the momentum principle. The spring was then recalculated and near the bottom. The changes in each form of energy are calculated as well. Here is a video showing the computational model. The first graph is showing the change in energy versus time. Later on, I will show the other two graphs that were created from this computational model that demonstrated the x and y positions as a function of time. Here is the first graph from the computational model, which demonstrates the change in energy versus time. The gravitational potential and the spring potential energies switch back and forth throughout the model since they oscillate in opposite directions. The kinetic energy also shows some oscillation since the object speeds up and slows down throughout its motion. The total change in energy is shown to be nearly flat, showing that there is no change in the total energy for the entire motion of the object. Here are the graphs showing the observed versus predicted models and their positions versus time. In both graphs, we can see that there is some slight deviation, more so in the y position graphs, which could be due to the fact that I used the x coordinates for the period of oscillation to find my spring constant. What does it mean? First, The energy principle satisfied? Looking again at the graph showing the change in energy versus time, we can see that the line for total change in energy is nearly flat or zero. Since we took into account the spring object and Earth as our system, we can say that our work or change in energy will be equal to zero. Therefore, since the line demonstrates such outcome, we can say that the energy principle is satisfied. Second, compare and discuss the period of oscillation from the X and Y position data. I have calculated both oscillation time periods, and there is a big difference between the both of them. This can have quite an effect on the outcome because depending on which position coordinate we wish to use, the spring constant is obtained using those numbers. Therefore, the best way to approach a situation like this is to try and find an average between both oscillation periods in order to reduce the change of deviation. Thank you.